Hi, in this video I'm going to talk about feature engineering for three types of data: numerical data, categorical data, and image data. And remember that we have already discussed the textual data processing in a previous video, so if you don't remember what was discussed there, or if you're in need of doing the textual data analysis and you want to do the data pre-processing, I refer you to that video on how to extract information from textual data. Okay, let's get started. And before diving deep to the concepts, let's clarify the basic definition of features. A feature is a numeric representation of raw data. And one thing that you should know is that there are many ways that one can turn raw data in numeric measurements. That is why features can end up looking like a lot of things. Naturally, features must derive from the type of data that is available. Perhaps less obvious is the fact that they're also tied to the model. And what do I mean by that is that some models are more appropriate for some type of features and vice versa. Also remember that the right features are relevant to the task at hand and should be easy for the model to ingest them. So there are so many things going on here. And it already shows that the feature engineering is not an easy, straightforward task necessarily. There are several things that you need to keep in mind. What is the type of data that you're dealing with? How you need to process that? And you should always have in mind that what is the model that you're processing this data for? How should you change the data? What are the features that you need to pick? And that is also combined in a sense so that what is the task you want to do, and that has a direct effect on what type of model you're picking, and then that has also a direct effect on how you're doing the feature engineering. Okay, I think we are clear here. So one other thing that you also need to remember is that the number of features is also very important. If there are not enough informative features, then the model will be unable to perform the task that we originally decided that we want to do. On the other hand, if there are too many features, or if most of what we have at hand are irrelevant, then the model will be more expensive and tricky to train. Something might go south in the training process that impacts the model's performance. If I want to put it in one single sentence, feature engineering is the process of formulating the most appropriate features given the data, the model, and the task. Okay, so let's start with the type of data that we may find easier than any other type of data. So before getting to the text, and we have already discussed that, or image data, let's start with the numeric data. And this may come, the numerical data, from a variety of sources. It could be a geolocation of a place or a person. It could be the price of a purchase. It could be, for example, the measurement from a sensor or traffic count. So we get the numerical data from all sources and all places, and probably that is one of the most used type of data, and we actually convert many other forms of data to numeric data to be able to deal with them better in machine learning. And numeric data is already in a format that is easily ingestible by mathematical models. So they are, as I said, easier to handle for the models that we are dealing with. And this doesn't mean that, so okay, now they're in this format that the machine understands, we don't need to do the feature engineering anymore. Good features not only represent the salient aspects of the data, but they also need to conform to the assumptions of the model. So that is why we need to do the transformation after all. And that is why this feature engineering for numerical data are actually fundamental. So let's see what are the steps and what can we do. The first sanity check that we do for the numerical data is to ask ourselves whether the magnitude matters or not. Do we just need to know whether it is positive or negative, or perhaps we only need to know the magnitude at the very coarse granularity? This sanity check is particularly important for automatically occurred numbers such as counts, and that's with that I mean, for example, the number of daily visits to a website or the number of reviews uh, performed for a restaurant. And after we did that, the next question is the scale of the features. What are the largest and smallest values? Do they span several orders of magnitudes? Models that are smooth functions of input features are sensitive to the scale. And what do I mean by that? This is what I have it here on the slide. For example, a simple linear function of the input x and the output of this and the scale of its output depends directly on the scale of the input. Other examples include k-mean clustering, nearest neighbor methods, radial basis functions, kernel, and anything and everything that uses Euclidean distance. For these models and modeling components, it's often a very good idea to normalize the features so that the output stays on an expected scale. Logical functions, on the other hand, are not sensitive to the input feature scale. Their output is binary no matter what the inputs are. For instance, the logical AND takes any two input variables and the output 1 if and only if both inputs are true. And let me see, another example that I can give you of a logical function is, for example, the step function. And that is like, is input greater than 5 or not? And decision tree models consist of a step functions of input features. That is why models based on space partitioning trees, and that is like decision trees, gradient boost machines, random forests, are not sensitive to scale. The only exception, and there is an exception, is that if the scale of the input grows over time, which is the case if the feature is an accumulated count of some sort, eventually it will grow outside the range that the tree was trained on. And this might be the case, and when it happens, it might be necessary to rescale the inputs periodically. Another thing that is also important to consider is the distribution of numeric features. And distribution is what is the thing that actually summarizes the probability of taking on a particular values. The distribution of input feature matters to some models more than the other ones. For example, the training process of a linear regression model assumes that prediction errors are distributed like a Gaussian distribution. This is usually fine except when the prediction target spreads out several orders of magnitude. In this case, the Gaussian error assumption likely no longer holds. And one way to deal with that is to transform the output target in order to tame the magnitude of the growth. Log transformations, and this is what we're going to discuss later in today's video, are a type of power transformation which takes the distribution of the variable closer to Gaussian. And one more thing that I want to let you know is that in addition to changing the features to make sure they are conforming to the assumptions of the model or the training process, sometimes we could also compose multiple features together and make a more complex feature. And the hope is that complex features could better capture important information in the raw data. Making the input features more eloquent in a sense allows the model itself to be simpler, easier to train and evaluate, and to make better prediction. But remember that taken to an extreme, complex features may themselves be the output of the statistical models, and this is the concept known as model stacking, which we are not going to discuss here. This was just for your information. Okay, now we are living in the age of big data. This is the talk everywhere. And in such an era, counts can quickly accumulate without bound. A user might put a song or a movie on infinite playback, or, for example, use a script to repeatedly check for the availability of tickets for a popular show, which will cause the play count of the website to go high very quickly. And when the data can be produced at high volume and velocity, it's very likely to continue a few extreme values. It's always a good idea to check the scale and determine whether to keep the data as raw numbers, convert them in binary values to indicate presence, or beam them into coarser granularity. And to tell you what I mean by all these things, we are going to have a look at a few examples. I don't know if you heard about the EchoNest test profile subset, which is the official user data collection for million signed datasets, and that contains full music listening histories of 1 million users on EchoNest. Here are some relevant statistics about the dataset. In this dataset, we have more than 48 million triplets of user IDs, song IDs, and listen counts. The dataset also contains 1,019,318 unique users when this data was collected, and 384,546 unique songs. Okay, now suppose our task is to build a recommender to recommend songs to the users. One component of the recommender might predict how much a user will enjoy a particular song. And since the data contains actual listen counts, should we take that as a target of our prediction? This would be the right thing to do if a large listen count means the user really liked the song, and a low listen count means that they are not interested in it. However, the data shows that while 99% of the listen counts are 24 or lower, there are also some listen counts in the thousands, with the maximum being 9,667. You can see the figure here. So this is the listen counts versus the occurrence. As you see, more than 10,000 triplets have greater counts with a few in the thousands. These values are really large, and if we were to try to predict the actual listen counts, the model would be pulled off by these large values. In the million song dataset, the raw listen counts is not a robust measure of user taste. And I tell you why. You see, users have different listening habits. Some people might put their favorite songs on infinite loop, while the others might save them only for a special occasion. We cannot necessarily say that someone who listens to a song 20 times must like it twice as much as someone who listens to it 10 times. A more robust representation of user preference is to binarize the count and clip all counts greater than 1 to 1. In other words, if the user listened to a song at least once, then we count it as the user liked the songs. This way, the model will not need to spend cycles on predicting the minutes differences between the raw counts. The binary target here is a simple and robust measure of user preference. Okay, so let's look at another example. Let's take the data from round 6 of the Yelp dataset challenge and think about a smaller classification problem. The Yelp dataset contains user reviews of businesses from 10 cities across North America and Europe, and each business is labeled with 0 or more categories. And the statistics are like this. There are 782 business categories. The full dataset contains roughly 1.6 million reviews and around 61,000 businesses. Restaurants and nightlife are the most popular categories if we consider the review count. And no business is categorized as both a restaurant and a nightlife venue, so there is no overlap between these two groups of reviews. And each business has a review count. So what is the task? The task here is to use a collaborative filtering, and you don't need to mind what the collaborative filtering. It's a way to build recommender systems to predict the rating a user to predict the rating that a user might give to a business. The review count might be a useful input feature because there is usually a strong correlation between popularity and good ratings. Now, the question is, should we use the raw review count or process it further? As you can see in this figure, and which is a histogram of all business review counts, we can see again the same pattern as in the listen counts in the previous example. Most of the counts are small, but some businesses have reviews in the thousands. Raw counts that span several orders of magnitudes are problematic for many models. In a linear model, for example, the same linear coefficient would have to work for all possible values of the count. Large counts could also destroy everything in an unsupervised learning method, such as K-mean clustering, which the model uses Euclidean distance as a similarity measure. A large count in one element of the data vector would overweigh the similarity in all other elements, which could throw off the entire similarity measurement. One solution is to contain the scale by quantizing the count. In other words, we group the counts into bins and get rid of the actual count values. Quantization maps a continuous number to a discrete one, and we can think of the discretized numbers as an ordered sequence of the bins that represents measure of intensity. And in order to quantize the data, we have to decide how wide each bin should be. And then the solution falls into two different categories, fixed widths or adaptive. And let's have a look at an example of each. Okay, with fixed width binning, each bin contains a specific numeric range. The ranges could be custom designed or automatically segmented, and they could be linearly scaled or exponentially scaled. For example, we can group people into age ranges by decade. 0 to 9 years old bin 1, 10 to 19 years old in bin 2, and so on and so forth. And to map from the count to the bin, we simply divide the widths of the bin and take the integer part. It's also common to see custom designed age ranges that better correspond to the ages of our life, like 0 to 12, 12 to 17, 18, 24, I don't know, and all these categories. When the numbers span multiple magnitudes, it may be better to group by powers of 10. For example, 0 to 9, 10 to 100, 100 to 1000, 1000 to 10,000, and so on and so forth. The bin widths grow exponentially, going from O of 10 to O of 100 to O of 1000 and beyond. And to map from the count to the bin, we take the log of the count. Exponential width binning is very much related to the log transformation, and we're going to discuss that, as I said, again in this video later. We also have quantile binning. And let's see what do we mean by that. Fixed width binning is easy to compute, but if there are large gaps in the counts, then there will be many empty bins with no data. This problem could easily be solved by adaptively positioning the bins based on the distribution of the data. And this can be done using the quantiles of the distributions. And what are the quantiles? Quantiles are the values that divide data into equal portions. For example, median divides the data into halves. Half of the data points are smaller and half of them are larger than the median. The quartile divide the data into quarters, decile into tenths, and etc. In this example here, you can see how the decile of the Yelp Business Review counts are defined. Okay, now that we talked about this, and I already mentioned log transformation a couple of times, let's see what do I mean by that. A log function is the inverse of the exponential function. The log function maps a small range of numbers between 0 and 1 to the entire range of negative numbers from minus infinity to 0. The log function compresses the range of large numbers and expands the range of the small numbers. The larger x is, the slower log of x increments. And this is easier to digest if you look at the plot here. Notice that how the horizontal x values from 100 to 1000 gets compressed into just 2 and 3 in the vertical y range, while the tiny horizontal portion of x values less than 100 are mapped to the rest of the vertical range. The log transformation is a powerful tool for dealing with positive numbers with a heavy tail distribution. And a heavy tail distribution places more probability mass in the tail range than a Gaussian distribution. It compresses the long tail in the high end of the distribution into a shorter tail and expands the low end into a long head. In this figure, we can see the comparison between the Yelp Business Review accounts before and after the log transformation. So the top one doesn't have the log transformation, the bottom one has the log transformation. The y-axis are now both on normal linear scale. The increased bin spacing in the bottom plot between the range 0.5 and 1 is due to there being only 10 possible integer counts between 1 and 10. And notice that the original review counts are very concentrated in the low count regions, with the outliers stretching out above 4,000. After log transformation, the histogram is less concentrated in the low end and more spread over the x-axis. Okay, now let's talk about another aspect of feature engineering, that is feature scaling or normalization. You see, some features like latitude or longitude are bounded in values. Other numerics, such as counts, may increase without bounds. And models that are smooth functions of the input, such as linear regression, logistic regression, or anything that involves a matrix, are affected by the scale of the input. Tree-based models, on the other hand, couldn't care less. If your model is sensitive to the scale of the input features, feature scaling could help. And as the name suggests, feature scaling changes the scale of the features. Some people also call it feature normalization, and feature scaling is usually done individually for each feature. Okay, now we talked about how manipulate features to some extent. Now let's talk about another important thing, which is called feature selection. Feature selection techniques prune away non-useful features in order to reduce the complexity of the resulting model. And the end goal here is a parsimonious model that is quicker to compute with little or no a degradation in predictive accuracy. In order to arrive at such a model, some feature selection techniques require training more than one candidate model. In the other words, feature selection is not really about reducing the training time. In fact, some techniques increase the overall training time, but it is about reducing the model scoring time. Roughly speaking, feature selection falls into three different classes: filtering, wrapper methods, and embedded methods. And we are going to talk about each of them in details. So let's start with filtering. Filtering techniques pre-process features to remove ones that are unlikely to be useful for the model. For example, one could compute the correlation or mutual information between one feature and the response variable and filter out the features that fall below a certain predefined threshold. And one thing that you should know is that filtering techniques are really much cheaper than the wrappers. It's just dropping stuff. Techniques that we're going to talk about next do not take into account the model being employed. And that's why they may not be able to select the right features for the model. And it is best to do the pre-filtering conservatively, so as not to inadvertently eliminate useful features before they even make it to the model training step. So if I want to put that in a very small nutshell, filtering is moving the things that you think are not necessarily, but you need to be cautious because you may lose the features that are actually important for your model. So treat cautiously, just remove the things that you're really sure that are not going to be useful for you. Now let's move to the wrapper methods. And these techniques that are quite expensive, they allow you to try out subsets of features, which means that you won't accidentally prune away features that are uninformative by themselves, but useful when taken in combination. The wrapper method treats the model as a black box that provides a quality score of the proposed subset for the features. There is a separate method that is iteratively refines a subset. And in this video, we are not really going to use Python packages, but this is for you to know if you want to do certain type of feature engineering, what to look for. And final method that we're going to discuss here is the embedded methods. These methods perform feature selection as part of the model training process. For example, a decision tree at the end performs feature selection because it selects one feature on which to split the tree at each training step. Another example is the L1 regularizer, which can be added to the training objective of any linear model. Embedded methods incorporate feature selection as part of the model training process. They are not as powerful as wrapper methods, but they are nowhere near as expensive. So it is somehow the middle ground between the filtering and the wrapper method. Compared to filtering, embedded methods select features that are specific to the model. In this sense, embedded methods strike a balance between computational expenses and quality of the results. Okay, so I think we can close it here with the numerical data and how to do feature engineering for them. And now we move to the categorical variables. A categorical variable, as the name suggests, is used to represent categories or labels. For example, a categorical variable could represent major cities in the world, I don't know, the 4 seasons in a year, or the industry, for example, oil, travel, technologies of a company. The number of category values is always finite in a real-world data set. The values may be represented numerically, and you remember we already discussed about these categorical variables before in one of our earlier videos. However, and this is the difference between the numeric variables, is that the values of a categorical variable cannot be ordered with respect to one another. Oil is not greater nor less than travel as an industry type. And that is why these types of data are called non-ordinal. A simple question can serve somehow as a litmus test for whether something should be a categorical variable or not. So you should ask yourself, does it matter how different two values are, or only that they are different? A stock price of $500 is 5 times higher than a price of $100. So the stock price should be represented by a continuous numeric variable. Whereas the industry of the company, oil, travel, tech, etc., should probably be categorical. Uh, Large categorical variables are particularly common in transactional records. For instance, many web services track users using an ID, which is a categorical variable with 100 to 100 millions of value, depending on the number of unique users of the service. The IP address of an internet transaction is also another example of large categorical variable. The vocabulary of a document corpus can be interpreted as a large categorical variable, with the categories being unique words. It can be computationally expensive to represent so many distinct categories. If a category, for example, a word, appears multiple times in a data point, which is our document, then we can represent it as a count and represent all of the categories through their count statistics. And this is what we call bin counting. The categories of a categorical variable are usually not numeric. For example, eye colors could be black, blue, brown, etc. That's why an encoding method is needed to turn these non-numeric categories into numbers. And it is somewhat tempting to simply assign an integer, say 1 to k, to each of k possible categories, but the resulting values would be orderable against each other, which should be not permissible for categories. So let's look at some alternatives. The first one that I'm going to talk about is hot encoding, and you may have already used that in some of your previous projects. So as I said, rather than assigning 1 to k to different k categories, one better method is to use a group of bits, and each bit represents a possible category. If the variable cannot belong to multiple categories at once, then the only one bit in the group can be on. And this is called hot encoding and is implemented in scikit-learn. I don't know if you probably have used it in the hot encoder. And each of these bits is a feature. So a categorical variable with k possible categories is encoded as a feature of vector of length k, and this is what you're seeing here. Hot encoding is quite simple to understand, but it uses more than one bit. It uses one more bit than is strictly necessary. For example, if we see k minus one of the bits are 0, then the last bit inevitably is 1, because the variable must take one of the k values. And mathematically, we can write this as the sum of all bits might equal to 1. That's why we have a linear dependency here. Now, linear dependent features can make the same predictions, so we need to jump through extra hoops to understand the effect of a feature on the prediction. And what I mean by that, basically several combinations of different features could end in the same result, and we are not always sure what is it that we are interpreting at the end of the model. Another way of doing this encoding is called dummy coding. And if you remember, I just said in a few seconds ago, the problem with hot encoding is that it allows for k degrees of freedom, while the variable itself needs only k minus 1. Dummy coding removes the extra degrees of freedom by using k-1 feature in the representation. And how that is done is basically they throw one feature under the bus, and that is represented by the vectors of all 0. And we call that as the reference category. I go back to the previous slide so you have a better understanding. The table here, we have 3 cities: San Francisco, New York, Seattle. And E1 is 1, E2 is 0, and E3 is 0 for San Francisco. And you see one of these positions are assigned 1 for each of the cities. For San Francisco, it's E1, for New York, it's E2, and Seattle, it's E3. But we have 3 digits here, one more than what we actually need. The next one, we basically kept Seattle as a reference point with 0, 0, and then New York on the second place, the digit is 1, and San Francisco on the first. So it is, as you see, simplify the matters, and at the end it will help with the interpretation of the model. Okay, so let's move on. As I said, the outcome of modeling with dummy coding is more interpretable than one hot encoding, and I see the example here. So let's see, it's not a full table, just give you an idea of what I'm talking about. Let's say we have some data about the apartment rental prices in 3 cities: San Francisco, New York, and Seattle. And we want to train a linear regression to predict rental price based solely on the identity of the city. Basically, what city, what is the price? And linear regression models are normally like y equals w1x1 plus up to wnxn, but we also throw in a value called intercept. So y can be a non-zero values when the x's are zeros. So with one hot encoding, the intercept term represents the global mean of the target variable, that is rent. And each of the linear coefficients represent how much that city's average rent differs from the global mean. With dummy encoding, the bias coefficient, that b, represents the mean value of the response variable y for the reference category, which in this example is the city in New York City. The coefficient for the ice feature is equal to the difference between the mean response value to the ice category and the mean of the reference category. And you can see pretty clearly in this table how these methods produce very different coefficients in the linear models. Another encoding method for categorical variable is called effect coding, and at the end it is very much similar to the dummy coding, with the difference that reference category is now represented with vectors of all -1s and not zeros. And as you see, it's quite similar, but at the end the results in linear regression model, for example, are much simpler to interpret. So now that we quickly browse different type of encoding, let's see what are the pros and cons of different categorical variable encodings that we already discussed. Okay, so let's start with one hot encoding. One hot encoding is redundant, which allows for multiple valid models for the same problem, and this non-uniqueness is sometimes problematic for interpretation. But the advantage, on the other hand, is that each feature clearly corresponds to a category. Moreover, missing data can simply be encoded as all 0 vectors, and the output should be the overall mean of the target variable. But when we get to the dummy coding, it is not redundant like one hot encoding, and this make it possible to have unique and interpretable models. But there is a downside to dummy coding as well, that it cannot easily handle missing data, since the all 0 vectors is already mapped to the reference category. And it also encodes the effect of each category relative to the reference category, which may look strange a bit. And effect coding, similar to dummy coding, is not redundant, and it ends in unique and interpretable models. Effect coding also is avoiding the problem we had with dummy coding with reference category being all zeros and then missing values are going to be the problems by using a different code for the reference vector. But the vector of all minus ones is a dense vector, which is expansive for both storage and computation. And for this reason, popular machine learning software packages such as Pandas and scikit-learn prefer dummy coding or one hot encoding instead of effect coding. And one thing you need to remember is that all these three encoding techniques break down when the number of categories becomes very large, and then you need different strategies to handle such extremely large variables. Automated data collection has caused these large categorical variables in some extent. And this is common in applications such as targeted advertising and fraud detection. In targeted advertising, for example, the task is to match a user with a set of advertisements. Features include a user ID, website, domain for the ad, search query, current page, and all possible pairwise conjunction of those features. And each of these is a very large categorical variable. The challenge is to find a good feature representation that is memory efficient yet produces accurate models that are fast to train. Sounds like an impossible mission, right? So what are the existing solutions? Existing solutions could be seen as two different categories. First, you should not do anything fancy with encoding. Use a simple model that is cheap to train. Feed one hot encoding into a linear model. It could be logistic regression, linear support vector machine, and lots of machines. Then compress the features. There are two different choices, and we're going to discuss a bit about them. Feature hashing, which is popular with linear models, and bean counting, popular with both linear models and, for example, trees. And as we see, they are all having pros and cons. So let's discuss the solutions first, and then we're going to get to the trade-offs. So let's start with the feature hashing. A hash function is a deterministic function, and this function maps a potentially unbounded integer to a finite integer range between 1 and n. And since the input domain is potentially larger than the output range, multiple numbers may get mapped to the same output. This is called a collision. A new uniform hash function ensures that roughly the same number of numbers are mapped into each of m beans. Visually, we can think of a hash function as a machine that intakes numbers of balls or keys and routes them into one of m beans. And balls with the same number will always get routed to the same bean. Sorry. And this maintains the feature space while reducing the storage and processing time during machine learning training and evaluation cycle. And this is what you see in this figure. Hash functions could be constructed for any object that can be represented numerically: numbers, strings, complex structures, etc. When there are very many features, storing the features vector could take up a lot of space, and feature hashing compresses the original feature vector into an m-dimensional vector by applying a hash function to the feature ID. For instance, if the original feature were words in a document, then the hash version would have a fixed vocabulary size of m, no matter how many unique words were there. And this is what is useful in many different scenarios. Feature hashing could also be used for models that involve the inner product of feature vectors and coefficients, such as linear models or kernel methods. there's one downside to feature hashing, and that is the hashed features being aggregates of the original features are no longer interpretable, so we cannot really interpret what is it that having an impact. And this is what I already said. The pros is that it could be used for models that involved feature vectors and coefficients. On the other hand, we lose interpretability. Okay, now let's get to the second idea, and that is bean counting. Bean counting, the idea behind bean count is actually pretty simple. Rather than using the value of the categorical variable as the feature, instead use the conditional probability of the target on their value. In other words, instead of encoding the identity of the categorical value, we compute the association statistics between the value and the target that we wish to predict. Let's explain it more. Let's provide more understanding by going through the example I have here, and probably then it is more clear what I mean by bean counting. Bean counting assumes that historical data is available for computing the statistics. And in this table, the historical counts are aggregated for each possible value of the categorical variable. Based on the number of times the user Alice has clicked on any ad and the number of times she has not clicked, we can calculate the probability of her clicking an ad. And you can see here. Similarly, we can compute the probability of a click of any query at domain combination. At training time, every time we see Alice, we can use her probability of click as the input feature to the model. And the same goes for query hash at domain pairs like that we have here. Okay. Now let's get to the elephant of the room, the image data. Our brains are hardwired to rapidly evolve our abilities to process visually and auditory signals. Language skills, on the other hand, are learned. They take months to develop and years to master. Many people take the development of their visions and hearing for granted, which is like maybe you're born like that, but all of us have had to intentionally train our brains to understand and use the language. So you see the difference. For learning the images, for recognizing the images, we don't really try hard. They just come to us. But if you want to learn a new language, it may take some good years. But the interesting part is that it is different for the machines. We have made, when it comes to the machine learning, we have made a lot of progress when it comes to the text analysis application than image or audio. Think about the problem of search, for example. Now, for several years, we have used a relative success in information retrieval and text search, whereas when it is about images and audios, we are still not there to be able to search them efficiently. And there is still a work in progress. The difficulty of progress is directly related to the difficulty of extracting meaningful features from this image or audio type of data. Machine learning models require semantically meaningful features to make semantically meaningful predictions. In text analysis, particularly for languages such as English, where a basic unit of semantic meaning, a word, is easily extractable, progress could be made much faster. Images and audios, on the other hand, are recorded as digital pixels or waveforms, and a single atom in an image is a pixel. In audio data, it's a single measurement of the waveform intensity. This, at the end, contains much less semantic information than a word, for example, in the text data. So that is why the job of feature extraction and engineering is much more challenging when we're dealing with image and audio than the text. And in the last 20 years, computer vision research and focus on manually defining pipelines for extracting good image feature. For example, image feature extractors such as SIFT and HOG, and we're going to talk about them later, were the standards. Recent developments in deep learning research have extended the reach of traditional machine learning models by incorporating automatic feature extraction in the base layers. And this essentially replaced the manual labor that would go into defining the feature image extractors. And of course, this manual work is still there, just abstracted further into this modeling beast. So let's see. Let's start by asking ourselves a question. What are the right features to extract from an image? The answer, of course, depends on what we're trying to do with those features. Let's say the task is image retrieval, and we are given a picture and asked to find similar pictures from the database of images. We need to decide how to represent each image and how to measure the differences between them. Can we just look at the percentage of different colors in the image? For example, here we have two pictures having roughly the same color profile, but very different meanings. One looks like a white cloud in the blue sky, and the other one is a flag of Greece. So color information is probably not enough to characterize an image. Another simple idea is to measure the pixel value differences between images. First, we can resize the image to have the same width and height. Then each image is represented by the matrix of pixel values. Then the matrix could be stacked into one long vector, either by row or column. And then the color of each pixel, let's say RGB encoding, is now a feature of the image. Finally, we measure the Euclidean distance between long pixel vectors, and well, with such an approach, we definitely could distinguish between the Greek flag and the white clouds, but it is still too simplistic similarity measure. For example, a cloud could take on 1,000 different shapes and still be a cloud. It could be shifted to the side of the image, or half of it might lie in a shadow. Still, these are the clouds. All these transformations would increase the Euclidean distance, but they shouldn't change the fact that the picture is still of a cloud. And the problem is that individual pixels do not carry enough semantic information about the image. So they are bad atomic units for the analysis. Okay, so now let's discuss some traditional feature extractions method or manual feature extraction methods, which are SIFT and HOG. In 1999, computer vision researchers figured out a better way to represent images using the statistics of image patches. The scale invariant feature transform, or SIFT, was originally developed for the task of object recognition, and that involves not only correctly tagging the image as containing an object, but also pinpointing its location in the image. The process involves analyzing the image at a pyramid of possible scales, detecting interest points that could indicate the presence of the object, extracting the feature, and it's called image descriptors in the computer vision, and then determining the pose of the object. Over the years, the usage of SIFT expanded to extract features not only for interest point, but across the entire image. The SIFT feature extraction procedure is very similar to another technique that is called histogram of oriented gradients, that is called HOG. Both of them essentially compute the histograms of gradient orientations. So, what is image gradients? To do better than raw pixel values, we have to somehow organize the pixels into more informative units. Differences between neighboring pixels are often very useful. Pixel values usually differ at the boundary of the object when there is a shadow within a pattern or on a textured surface. And the difference in value between neighboring pixels is called an image gradient. So this is an image gradient. And the simple way to compute the image gradient is to separately calculate the differences along the horizontal and vertical axes of the image, then compose them into 2D vectors. There are 2D gradient filters, but sometimes we can use the 1D as well, depending on the example. Then to apply a filter to an image, we should perform convolution, and it basically involves flipping the filter and not taking the inner product with the smaller patch of the image, then moving to the next patch. It's actually very similar to what we are doing in convolution. It's exactly not very similar what we are doing in convolutional neural networks. And convolutions are very common in signal processing. A vector can be completely described by its direction and magnitude, and the magnitude of the gradient indicates how much the pixel value change around that pixel. The direction or the orientation of the gradients depends on the relative size of the change in the horizontal and vertical directions. Okay, in this example of simple gradients that is composed of vertical and horizontal gradients, each example is an image of 9 pixels, and each pixel is labeled with a grayscale value. Basically, the smaller the number corresponds to the darker color. The gradient for the center pixel is shown below the image. The image on the left contains horizontal stripes, as you can see, where the color only changes vertically. Therefore, the horizontal gradient is 0 and the gradient is non-zero vertically. The center image, on the other hand, contains vertical stripes. Therefore, the horizontal gradient is 0, and the image on the right contains digital stripes, and gradient is also diagonal stripes, and the gradient is also diagonal. The definition works on this toy example, but does it work on the real example as well? In this figure, it's an example of a cat from scikit image, and its horizontal and vertical gradients. Since the gradients are computed at every pixel location of the original image, we end up with 2 new matrices, each of which could be visualized as you see here as an image. Notice that the horizontal gradients pick out strong vertical patterns, such as the inner edges of the cat's eye, while the vertical gradient picks out strong horizontal patterns, such as the whiskers or the upper-lower lids of the eyes. This might seem a little paradoxical at first, but it makes sense once we think about it a bit more. The horizontal gradient identifies changes in the horizontal direction, and a strong vertical pattern spans multiple y pixels at roughly the same x position. Hence, vertical patterns result in horizontal differences in pixel values. That is why what our eye detects as well. Individual image gradients can also pick out very small differences in an image neighborhood. But our eyes see bigger patterns than that. For instance, we see an entire cat's whisker, not just a small section. The human vision system identifies patterns in a region, so we still have more work to do to summarize the image gradients in a neighborhood. How exactly might we summarize vectors? A statistician would answer, look at the distribution. Sift and Hogg both take this part, and in particular they compute histograms of gradient vectors as image features. A histogram divides data into bins and counts how many data points are in each bin. This is an empirical distribution. Normalization ensures that the counts sum to 1. Well, it is true that Swift and Hawk went a long way toward defining good image features. However, the latest gains in computer vision have come from a very different direction, and that is deep neural network models. The breakthrough happened at the ImageNet Large Scale Visual Recognition Challenge in 2012, where a group of researchers from the University of Toronto nearly halved the error rate of the previous year's vision, and they branded their method as deep learning to emphasize that, unlike the previous architecture, neural network models, the latest generation contains many layers of neural networks and transformation stacked on top of each other. On surface, the mechanism of a stacked neural network, deep neural network in short, appears very different from the image gradient histograms of Swift or Hawk. But visualization of AlexNet, one of these deep learning architectures, and I'm going to only talk about that, but at the end, all the architectures are similar, so you learn this, you get the whole idea. So getting back to the AlexNet visualization, the first few layers are essentially computing the edge gradients and other simple patterns, very much like Swift and Hawk. And then subsequent layers combine local patterns into a more general global pattern. The end result is a feature extractor that is much more powerful than what we had before. The infrastructure of stacked layers of neural network is not new, but training such complex models requires a lot of data, a lot of computing power, and that was not available to us until very recently. For example, the ImageNet dataset contains a labeled set of 1.2 million images from 1,000 casas. Modern GPUs has sped up matrix vector computations, which at the end lie at the inner core of many machine learning models, including neural networks. And the success of deep learning methods is, as you have heard in many different places, because of an amount of data and lots of GPU hours. Deep learning architectures could be composed of several different layers. And AlexNet that I'm going through as an example here is containing fully connected convolutional response normalization and max pooling layer. Let's see what do I mean by that. At the core of all neural networks are linear functions of the input. Logistic regression, which we encountered before in previous videos, is an example of a neural network. A fully connected neural network is simply a set of linear functions of all of the input features. The fully connected layers is so named also because every input can be used in every output. And as you can see here, a fully connected neural net can be represented by a complete bipartite graph where every node in the input is connected to every node in the output. Fully connected layers contains the maximum possible number of parameters, and that's why they are actually quite expensive. Such a dense connection allows the network to detect global pattern that could involve all the input. That is why the last two layers of AlexNet are fully connected layers. The outputs are still independent from each other, conditioned on the inputs. So this is the first layer, some of the layers. And then let's get to the next one, which is convolutional layers. In contrast to fully connected layers, a convolutional layer uses only a subset of input for each output. The transformation moves across the input, producing outputs using a feature at a time, a few features at a time. It is easiest to explain the intuition behind convolution using an example from signal processing. Let's imagine we have a black box, and to see what the black box does, we pass a single unit of stimulus through it. Then we record whatever the output looks like on a little sheet of paper. We wait until there's no more response to the original stimulus, and then the resulting function over time is the response function, and let's call it g of t. Now, imagine we have some crazy wild signal called f of t. We proceed and feed it to the black box. At time t0, f of 0 interacts with the black box and produces f of 0, and then that is multiplied by g0. At time t, f1 enters the black box, gets multiplied by g0. At the same time, remember that the black box continues to respond to the previous signal f0, which is now multiplied by g1 because the time is changed. So the total output as time t is f0 multiplied by g1 plus f1 multiplied by g0. At time 2, the situation gets even more complicated, with f2 entering the picture, and f0 and f1 continue to generate that response, and at the end, this is the total output. So this is more or less how the convolution is working. When computing the value of a convolution at a particular time step, we multiply the overlapping signals together and then sum them up. The scalar multiplication and summation, typical things. And the convolutional operator captures the effects of a linear system quite beautifully. So what is the intuition behind this convolution? The convolution operators, as I already mentioned, captures the effect of a linear system which multiplies the incoming signal with its response function, summing over current response to all past input. In the example I just said, g of t is used to denote the response function and f of t the input. But since the convolution is symmetric, it doesn't matter which is the response and which is the input. The output is simply a combination of both. And g of t is also known as a filter. So this is what we are talking about when we say we are using a filter in the convolution. Images are two-dimensional signals, so we need a 2D filter, and a 2D convolutional filter extends the 1D case by taking the integral over two variables. Since digital images have discrete pixels, the convolution integrals becomes discrete sums. Furthermore, since the number of pixels is finite, the filter function only needs a finite number of elements. In image processing, we also call this 2D mask, a 2D filter, a kernel, or a mask. And when applying a convolutional filter to an image, you do not necessarily define a giant filter that covers the entire image. Rather, as you see here, we formulate a small filter covering just a few pixels by a few pixels and apply the same filter across the image, shifting over the horizontal and vertical pixel direction. The output of a neural net is often passed through another nonlinear transformation, also known as the activation function. Common choice are tan, edge function, a smooth nonlinear function bounded between -1 and more, a sigmoid function, a smooth nonlinear function between 0 and 1, or what is known as a rectified linear unit or a ReLU. A ReLU is a simple variation of a linear function where the negative part is zeroed out. In other words, it trims away the negative values but leaves the positive part unbounded, and the range of ReLU extends from 0 to infinity. The ReLU transformation has no effect on non-negative functions such as the raw image or Gaussian filter. However, a trained neural net, whether fully connected or convolutional, will likely output negative values. And AlexNet uses ReLU instead of other transformation because they claim that it is faster convergence during training. It applies ReLU to every convolutional and fully connected layer. And one final layer that we're going to discuss about is the pooling layer. A pooling layer combines multiple inputs into a single output. As the convolutional filter moves across an image, it generates an output for every neighborhood under its lens. Pooling forces a local image neighborhood to produce one value instead of many, and this reduces the number of outputs in the intermediate layers of the deep learning network, which effectively reduces the probability of overfitting the network to training data. There are multiple ways to pool inputs: averaging, summing, which is like computing a generalized norm, or taking the maximum values. Pooling moves across the image or intermediate output layers. Okay, so that was in short an insight of doing feature engineering for image data, and let me wrapping it up here. Now we can build on the intuition gained to better understand why the most straightforward and simple image feature which not always be the most useful for performing tasks such as image classification. Instead of representing each pixel as an atomic unit, it's more important to actually consider the relationship pixels have with each pixel near them. We can adapt techniques developed for other tasks such as sift and hog to better extract feature across entire image by analyzing gradients in the neighborhoods. The next leap forward in recent years is to apply deep neural networks to computer vision to push feature extraction of image even further. The important thing that you should remember is that deep learning stacks many layers of neural network and transformation on top of each other. And some of these layers, when examined individually, begin to tease out similar features that could be identified as building blocks of what we have as human visions, that are defining lines, gradients, and color maps. And by this, I think we can close the feature engineering video. I wish you good luck with your assignments, and I see you in the next lecture.